Now that we've talked about a bunch of different types of integrals, double, triple, line integrals, let's try to piece them together as we may have thought of the fundamental theorem of calculus and fundamental theorem of line integrals. We start piecing things together. That's what really theorems are for, to piece things together. So if we have a curve C in the plane, it has positive orientation if it is transversed counterclockwise exactly once. If C is the boundary of a region D in the plane, C has positive orientation if when you transverse C, D is on the left. And we write C to equal the partial D or boundary of D in this situation. So if this is our region, D, then how would we find the boundary? Well, clearly the boundary should be this line somehow. And we want to be going counterclockwise. And how we know that it is a good boundary is as I travel on this curve C, if I'm on it, to the left is D. So if I'm here, I look to my left and I see D. Therefore, this is a good boundary. So it's not to the right, that would be not D, obviously. So we can write C to be equal to the boundary of D. So we come to one of our really important theorems, Green's theorem. Let C be a positively oriented, piecewise smooth, simple closed curve. A lot of things on the curve. In the plane, which bounds a region D. If P and Q have continuous first partials on the region containing D, then we have our integral over the curve P dx plus Q dy is equal to the double integral over D of the partial of Q with respect to x minus the partial of P with respect to y. All of this dA. Hopefully we can give a kind of intuitive proof for this, which I will do. Some notation. For a closed curve C, we write a circle around the integral over C, P dx plus Q dy, to imply that C has a positive orientation. Recall that writing the boundary of D for the boundary of D implies that the boundary of D has a positive orientation given our definition. So therefore we could rewrite Green's theorem as the double integral over the region D of partial of Q with respect to x minus the partial of P with respect to y dA equals the integral over the boundary of D, P dx plus Q dy. Now let's do an example. Suppose we are asked to solve this integral, the integral over the curve C of y plus e to the x dx plus 2x plus cosine of y squared dy, where C is the boundary of the region bounded by y equals x squared and x equals y squared. So let's actually look at that region. We do this, and here's our y, here's our x, and we get y squared equals x. And here we get y equals x squared. And so D would be our region right here. That's D. And C is if we went around this curve. So remember, in a counterclockwise fashion. Well, it's impossible to do this directly, so we're going to have to invoke Green's theorem. So we have our initial integral, and we use Green's theorem. Now, here is our Q. So we take the derivative with respect to x, which would just be 2. Plug the 2 in there. We have this integral, which is our P. We take the derivative with respect to y. We just get our 1. And we have 2 minus 1 dA. the double integral over the domain, which now let's set this up as dx dy. And as we would set up our normal double integrals, we have y squared, when we look at it from the x perspective, as our bottom, and square root of y as our top, and y would go from 0 to 1, because this is the point 1, 1, which we can simplify as the integral from 0 to 1 of square root of y minus y squared dy, and then we just can do that integral, and we get 1/3. So this very complicated integral here was so much simpler once we use Green's theorem. So it's really good to be able to start piecing our pieces together.